Hey folks, so welcome back to our discussion of hearing in the environment. Now, one of the things that we do need to kind of talk about is that there is an issue with using both ITDs and ILDs for sound localization. And this is what's known as the cone of confusion. So there is so basically, as we kind of talked about last time, when we talk about those different positions around the azimuth, depending on where a particular object is and is making noise, we will have a certain ITD or a certain ILD. Well, one of the things that's kind of interesting is that depending on that position, there are actually areas that will evoke the same ITD or the same ILD. And this is basically what we refer to as the cone of confusion. So basically, if we have an object that is eliciting a certain ITD within a particular region of space, you could get the exact same ITD from a slightly different position. So basically, this can make it very, very difficult for us to figure out where a sound is coming from. And here's kind of another way that we can actually look at it. So right here, you can kind of see in this three-dimensional space, we have our azimuth. So here we have 0 degrees at the center of the head. Here we have 60 degrees, 120, and 180. So that's the back of the head on the right side. And then over here we have the left side of the head. Now, what you're kind of looking at, these red lines are basically areas around the head that will evoke the exact same ITD or ILD. So and elevation does play a role with this as well. So if we are right about at least maybe about anything that's kind of falling on this line right here is going to evoke the same ITD. Another way of kind of looking at it is any items that share the exact same color will have the same ITD as well. This also is true for ILDs. So what this tells us is that there are a lot of different areas in space that will create the same interaural time difference or interaural level difference. So how on earth are we actually able to tell these different things apart? Well, there are a couple of different things that we can do. So one of the things that we can do is very simply turn our head. So for example, let's say here that we are listening to the sounds of these two different frogs. So this frog is located right here, a certain distance from the ear, about 45 degrees. Here, this green frog is also in a very similar position behind the head. So what's kind of interesting here is that both of these frogs' noises will evoke the same ITD as well as the same ILD, because at least in terms of the azimuth, they are equally distant from the ear. So if I briefly turn my head counterclockwise, I can basically kind of figure out that the noise I'm hearing is the blue frog and not the green frog. The problem is, though, that now I could potentially have another frog enter that cone of confusion. So turning our head very simply is one of the ways that we can disambiguate sounds, but it doesn't completely resolve the cone of confusion. So one of the things that also helps us is the shape and the form of our pinna. So if you get an opportunity, take a mirror and kind of take a look at your pinna. And if you have somebody in the house with you, go take a look at their pinna. Please ask them ahead of time and get their consent before you start looking at their ear in a weird way. But what you should notice is that in general, everybody's pinna are slightly different. They have different grooves. And it turns out that this is very, very important. This helps create what is called a directional transfer function. So the pinna enhance certain frequencies over others. In general, We do tend to find that higher frequencies tend to have their intensities enhanced a little bit relative to lower frequencies. So we know that the pinna can play a role with that. In addition to that, don't forget that the size of the head can also play a role. Remember that we mentioned that because your head is irregularly shaped, that can create a sound shadow that modifies the intensity of certain sounds. Additionally, even the upper body can actually do this as well. So this creates what we call a directional transfer function, or a DTF. This basically describes how the pinna, the ear canal, the head, and the torso actually change the intensity of sounds that have different frequencies that arrive in each ear from different locations. So some of these intensities will be amplified, or some of these frequencies will be amplified in intensity. Some of these frequencies will be dampened in intensity. Now, the reason that I asked you to look at people's ears is because everybody has a different pinna. And because of that, every person has their own directional transfer function, and they can use that to help locate sounds in space. So what you're looking at here are pinna shapes. As you can see, there is a lot of variability between people. And basically what this means is that the way that you locate sounds could have some idiosyncratic differences from how other people do. So how you locate sounds in space utilizing a DTF is completely unique and special to you and the way that your ears and your head and your upper body are shaped. Now, what you're kind of looking at here are directional transfer functions. So what's going on here, you are basically looking at measurements at the eardrum for sounds that are basically being played over a speaker about 30 degrees to the left and about 12 degrees up from the head. So what you're kind of seeing, so you have magnitude, you have intensity plotted against frequency. And what I really kind of want you to pay attention to is that these different sounds are not equally intense. Now, the speakers that these are coming from, they are equally intense, but you can kind of see that based on directional transfer functions, certain frequencies become amplified, particularly those at higher frequencies. Though certainly not all frequencies. It looks like this particular frequency just below 10,000 hertz was actually dampened. You'll also notice that lower frequencies don't really have they don't really get much of an amplification relative to those higher frequencies. Now, what you're looking at here is for a sound for a single point in space. Now here, you're basically looking at the exact same azimuth, but we're also starting to also include elevation as a factor of this. So, this basically provides us with some information to localize sounds. They're not symmetrical, and we can take into account the amplification of sounds, the elevation of sounds, and use our DTFs to basically figure out where a sound is coming from. So that's kind of one aspect of sound localization, figuring out where a sound is coming from. But we also need to potentially figure out how far away a sound is from us. Now, probably one of the simplest cues that we have is intensity. So generally, louder sounds, we typically will perceive them as being closer to us than sounds that are farther away. The problem with that is I'm sure you can certainly think of instances where you have heard very quiet sounds that were very, very close to you. So a really good example of this is my cat. So my cat has what I like to refer to as a whisper meow. It is a very, very soft little meow that basically sounds like he's whispering. He's kind of like, meow. And he will even do that if he is sitting right in front of me. And so it can be very, very difficult to use intensity as a cue. you could have something being very, very close, but it might be muffled by the surrounding environment. So distance or intensity is a good start, but it's not all that we need. And generally, we do find that focusing on the relative intensity of a sound becomes especially difficult as distance starts to increase because of something known as the inverse square law. So basically what we tend to find is that for sounds, the decrease in intensity that we experience is equal to the distance squared. So your book kind of gives you an example of this. So if I have a sound that's about 3 feet away, that is going to be more intense by about 6 decibels than a sound that's about 6 feet away. That same difference between 39 meters and 40 meters produces far less of an intensity change. So generally, as your distance from a sound source increases, the intensity decreases faster as well. So we have to use a few other things to help us out. So intensity is certainly one cue for how far away something is from us, but it's not the only thing. And generally, we will find that intensity tends to work best when we are moving towards an object or an object is moving towards us. So think about that, for example, with respect to something like Marco Polo. You basically figure out if you can find a person based on the intensity of the sound changing as you move through the environment. So intensity is one thing that we can use to judge how far away something is, but it's not perfect. The other big thing that we can do is we can look at the spectral composition of sounds. So because of some of the properties of the head and because of the properties of air, what we do tend to find is that higher frequencies will tend to decrease in energy more than lower frequencies do as sound waves travel from the sound source to the ear. So that's another thing that we can use to help us figure that out. Generally, high frequencies are a lot more likely to decrease in their energy versus a lower frequency sound, which, as we mentioned last lecture, has the ability to bend more. And because of that, it's less likely to degrade. So generally, as your textbook mentions, the farther away a sound source is, the muddier it sounds. So we lose those higher frequencies and we get those more middling frequencies, and we don't have as good sound quality. Now, the other thing that also does play a role are the relative amounts of what we call direct energy versus something like reverberant energy. So direct energy is a case where sound is directly coming from the source itself. Reverberant energy is the energy or the sound that you pick up after a sound source has basically bounced off of things like walls, other people, and so on. So basically, comparing how much of that is coming from the source to how much of this is coming from sound waves bouncing off of things, that reverberant energy. So here's kind of an example. So here, we've got this man who is sitting in the audience of a concert. And so one of the ways that he can actually figure out how far away something is from him is comparing direct energy to reverberant energy. So when somebody behind him is talking, he can hear the sound directly behind his head. That's not bouncing off of anything, and that in fact is a source of direct energy. Now, the singer is probably too far away from him to actually get all of that direct energy, so most of what he is going to hear is going to be a product of reverberant energy. So you can see that the sound from her voice and the sound from her guitar is bouncing off all these different types of sources in the environment. So generally what we will find is that if a sound source is close to you, as this man is, you're going to perceive a lot more of that direct energy. If the sound is farther away, you're going to get less direct energy, and you're going to get far more reverberant energy. And it turns out that those reverberations are really helpful for us figuring out how far away that sound is. So now let's move on and talk about some other aspects of sound. So we're going to start by talking about harmonics. So a lot of the different environmental sounds that we hear out in the world, including our own voices and musical instruments, have what is called a harmonic structure. So generally, here's how harmonics work. So if we are looking at a particular harmonic spectrum of somebody's voice or of a musical instrument, we are going to be able to identify what is referred to as a fundamental frequency. So a fundamental frequency is the lowest frequency of the harmonic spectrum. Any other frequencies that we hear to create that complex sound will typically be multiples of that fundamental frequency. So, for example, let's say that I was producing a sound at about 250 hertz. So the greatest amount of energy will be at that fundamental frequency, but I will also have multiples of that frequency. So there will be some energy at 500 hertz and 750 and 1,000 and so on. But what we'll tend to find is that most energy will be at the fundamental frequency and considerably less will be in those harmonic multiples. Now, your auditory system is very sensitive to the relationship between harmonics. And one of the ways that we can actually see this is with something that's called the missing fundamental effect. So one of the things that's kind of interesting is that if I play all of the harmonics of a sound, but I leave out the fundamental frequency, you will still hear the frequency that matches the fundamental frequency, even though it's not actually being played. So I'm going to go ahead and give you an example from our companion site, so you can kind of see this in real time. So I'm going to go ahead and turn up the volume so you can hear. We're going to go to the missing fundamental effect. So we're going to start by playing just a difference between a simple tone and a harmonic sound. So that's 250 hertz as a simple tone. Now I'm going to play 250 hertz with its different harmonic frequencies. So our fundamental frequency is 250 hertz. Here we have the second, third, fourth, fifth, and sixth harmonics, and they are all multiples of 250, and you can see that as we move from harmonic to harmonic, less energy is being used on those multiples. So that sounds a bit more complex than our simple tone of 250 hertz, and that's because those multiples contribute to that sense of complexity. So now let's go ahead and mess around with the missing fundamental. So let's go ahead and play that tone again, but this time I'm going to start removing some of the different harmonics, and let's see what happens. Okay, so now I'm going to play that, but I'm going to remove the 1500 harmonic. Oop. All right, so let me try that again. I think I have to start by removing the fundamental frequency first. Okay, so in this case, I took out the fundamental frequency. I've still got the second, third, fourth, fifth, and sixth harmonics, but you can still hear the frequency. Now, you'll notice that the quality of the tone is definitely different, so let's play it with the fundamental. Let's play it without. But the pitch is still the same. Now, what happens if I remove the second harmonic? Still sounds like 250 hertz to me. Now let's remove 750. I'm still getting it. The sound quality is definitely not as rich and complex as it was, but it's still matching that 250 hertz. Now let's get rid of 1000. Still sounds like it's at about 250 hertz. Now let's get rid of 1250. So now that I've removed 1250, this is the new fundamental frequency, and it's at 1500 hertz in this case. So you can see that there's a difference in pitch. So let's play that again. So you can see that there's a difference there. So your brain is really good at noticing the harmonics and the relationship between the harmonics, even when you get rid of the fundamental frequency. And we'll talk some more about this pretty soon.